There you go. Welcome back to another episode of Develop the Potential Electronics from Concept to Production. We're on episode 31 now. We've been streaming for quite some time now, and we're making a lot of progress designing a AC/DC switch mode power supply. And we're gonna continue doing a PCB layout. So let's jump right into it. This is where we left off, basically, last episode. And we were doing these traces here, so the higher current nets. And we're doing copper bores for the whole thing, which I think is a good approach, hopefully. Let's check it out later on, of course, to see if this is good, but for now I just get it started. Try not to worry too much about it. And I'm also, considering high current nets first, and then we do everything else later. I mean, at least going over everything else later. Because everything is routed, it's just a matter of taking care of every net, making sure that we have designed properly, and we know that these copper pores and these traces can handle, or that they can carry the current that they are exposed to, I guess. So we're actually making very good progress, I would say. Yes, last episode we looked at this. Wait, let me take that away a little bit so it's a bit easier. Yeah. We were working on this trace right here from, so this is on the coil, the primary side coil, down to the MOSFET drain channel, and up to this RCD clamp that is right here. And yeah, it's not very nice, this, so we need to look into a way to connect the two. I want a cleaner approach. But maybe first we should look into the schematic and then check what current do we have here. What's the best way to check that? And then I should maybe check my notes. Damn, I completely forgot that I've been taking notes of all of this. That's good. Yeah, like here, for instance, we know because of this high ohm resistors that the current through these components, so on these nets, are minimal, so very small, so we can just use default traces on them here. They don't have to carry a lot of current, so it's no problem for them to be the default or the minimum that we set. at 0.254, which is the default value also. Yeah, so not a problem at all, I would say. Down all the way down here too. What else? I think here, obviously, so here's only like 3 amps max or something, 2.7 I think we set the brownout protection or something. What else? Here too, very high ohm, not a problem. Question is really on these. So I think this should be copper pores all the way. Then maybe this one, which I did do some, when I did the RCD calculations, maybe I okay, no, nothing. Wait, I will bring up my notes. We're gonna get there eventually. We're very close with this design. I dare say. I dare say. Maybe not 100% production ready, but we're making a lot of progress. Just want to see my notes from before. Drain to source current. And the primary peak current is 1.23 ampere. And then the drain to source current 2.5 ampere. And if I look at this board setup and I check, so this copper, this top layer copper is 0.035. Is that one Aus copper to millimeter? Yeah. So that's 1 ounce of copper thickness on the top layer. IPC trace width calculator. To show the screen again here. So we got 1 ounce of thickness, ambient temperature of 25 degrees, and a temperature rise of 10 degrees Celsius. So an external. Oh wait, okay, here. So let's say 2.5. It has to carry that 1 ounce per square foot. Then 10, 25. And how long is this trace? I'll take that away, and then I will just trace it down like this. How do I select the whole? Select. How do I see the distance? How to see that length selected. So segment length, routed length. Okay, I think this should be this whole thing then. So 335 millimeter. So the trace width should be at least 1.06 millimeter. Almost 100 mil. So what about 1.25? Yeah, we could do it. I think we can do that. That's cleaner looking, at least, than having them through a via. Why can't I edit here? Maybe like that. So then this can handle, now it's 1.25, so even with some margin, and we have 2.5 ampere. So that's the current capacity of this trace right here. What else? And then here we just do the copper bore. Probably also could do this same length also on this net here. Could do that, but let's leave it like this for now. Let's check the schematic and I'll drink my tea a little bit. Now, the auxiliary winding will either be so it will be either 16 volt here. That's the VCC pin it's going to. So from here, will be minus or negative 60. While the reverse voltage cross drive is just the difference between. Selecting average current through diode and pulse current into VCC capacitors. So here. So this is powering the chip itself, right? The soft start or the internal, like initial start of this chip is through the zero crossing detection pin. It just starts it enough for the internal circuitry to power it itself when it switches off again. So whenever the secondary winding here in the MOSFET off state, then it's on here, 16 volts, and it will power this. The average gate current is therefore equal to 2.2 milliampere. But for instance, it's 16 volt here, and then across this 27K. 16 divided by 27 is 0.59. Milliampere. So let's see, we have selected a diode with a 1 amp rating here. Which means we could say it's probably even too much. Seems like we only need, wait, so if it's 16 here, over 27. That's 0.6 amps. I would argue that we can have a trace here that can carry up to 1 amp, since we set the diode to 1 amp. 1 amp rating for current 1 amp. Yeah. Why not? So this trace right here should be able to carry 1 amp, worst case. So we take our calculator once again. So 1 amp, the same thickness, the same temperature rise, ambient, and then the length of this net. So this and this and this. $76. So let's say 80. So the trace can be 0.3. So almost the default. And if this is lower, 50. Doesn't matter really, I guess. Just what changes: the voltage drop, the resistance, and the power loss. So 10. That's the only thing that changes. Okay, so 0.3. We can also just do 0.5. Use net class. Yeah, I can do it like this. And this one can be default then. You can just branch out from it to a lower trace. What else? here we can just leave default. So gate current. None of these are drawing a lot of current that we know. An optocoupler, for example, I mean, we take the current through the LED, this resistor, so 12 volts. You can check, just worst case, 12 volts divided by 825, which is 14.5 milliampere. Oh no, wait, no. Oh, divided by 825. Yeah, right. So milliampere, 14.5. 14.5 and then times the current transfer ratio, which was something. CTR. I don't know the exact value, but I'm pretty sure we can use default. It's not a lot of current here. I think we could even look at the feedback in 0.22 milliampere. Damn, I made so much noise. Notes, not noise. So notes. So much notes on this. I think it's pretty safe to say the rest of the traces here are quite low current. Maybe this. So the source. Supply voltage, charge current. Drain to source on resistance 0.31 or 0.29. I think it's safe to say we need to also have this longer trace between the source to this pin. I'm guessing. So let's just do it. Didn't need to have much, but just select all tracks net from 5. No. Okay. One 1.5. Because it would go through here, right? And then this way. Same current. It's not that pretty. I realize that. Honestly, maybe it would be better to rotate this. Like this. You would have the... Oh, maybe we should do that. That looks cleaner. It kind of looks like it makes more sense, honestly. That it would be like that. But that's really all the traces that we need to take care of, I think. This part to be out. So 12 volts divided by 9.5. Divided by 9,500. Which is 1.26 milliampere. So here and here 12 volts. 1.26. Or I mean 126. 9.5 milliampere. So 10 milliampere. Down here. This trace is so ugly though. Kind of want to route this way instead and then via up here and then back. Like that instead. Because why not? It's the only via that we have on the bots. Oh, the only trace on the bot layer. So let's see here. Now let's just put some copper on the top. Oops. Right, this one is not correct. It should be 0.8, 0.4, 0.84. Hmm. Maybe we should like this again. And these. Maybe they should just be traces rather. How big? Let's say they should carry 10 amps, then they should be 7.2 millimeter. How much is that? Oh boy. So let's do 4. Let's do 3, 2. So 2 amps. So 4 amps. 2 millimeter should carry, should have a current capacity of 4 amps. So let's do the same here. 2. Let's do the same. It looks nicer. It looks way nicer. Select. Two. Oh, okay. Da, 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 da. I wonder if I should move them a little bit down and kind of branch. Oops. Is it okay to do it like this? I wonder. Maybe if we do like this instead. It looks clean. It looks clean. This port maybe. And then here is very dense. Yeah, and then we have this porch. Here too. Okay, a bit extreme. Maybe this part down here. As we know, we don't really need that much current capacity down to these resistors. So if we have 12 volt here, we have very little current through here. So maybe this part. I don't really know if you need to do this. At all. Nah, look dumber. Looks kinda dumb. Or is it necessary? I mean, to me it looks like we've given it some thought, at least. I think that's good. So looking a bit at our rough layout plan, I think it correlates quite well. What do you think? It feels nice, at least, to have come this far with the design. Bit curious how it would look with green solder mask. So here we have the primary side, the terminals on both sides. Plug in the input to the input stage right here with bridge rectifier, input capacitor, RCD clamp circuit, the transformer, MOSFET, the regulator chip, and all necessary components for that. And here you have this Y-rated capacitor. Y-rated capacitor, yes. In order to protect. Oh, good question. I did take some notes on that. Anyways, then we have the optocoupler and the output, or the secondary side, the output stage. So the diode, output capacitor, then the load resistor, just for the sake of the example, then terminal, and then here the feedback network and the compensation network. And in the middle we have a isolation gap. I think that looks pretty alright. It's cool, at least. I enjoy it. So if you have any questions, feel free to drop them in the chat. Whatever it is, I'm excited for having more people in here talking about electronics, designing, having a good time. Talking about technology, all kinds of projects are coming up on this channel. So right now we're doing power electronics, which I really enjoy and which is my job also. Soon, at least. Electronics is my job. I'm not too specific right now, but at least we'll have way more projects in the future. Now we have power electronics. There will be other solutions, other ideas being realized on this channel for the sake of this community. So please join the Delta Potential. Put a like on this stream. Join the community. We're not many, but we're gonna be. That's a fact. Because I got a love and a passion for this stuff. And I'm gonna share it. I'm gonna spread that passion. And we're gonna build some cool stuff. And on that note, I'm gonna have a little bit of a break. I'm gonna make some more tea. I'll be right back. I hope you're here when I get back. 5-minute break. Okay, Back. I am back. Trying to think a little bit what if this is all right. I think maybe these vias might be too small to look into via sizing too in terms of current capacity. How do you think about that? Do you think current coming out of this pin right here via to this output capacitor to ground and then here How do you think about that? Let me also do check DRC. Missing connection between items where oh, right. Do, do, do. That's maybe the only thing that I'm thinking about, other than maybe moving things a little bit, space things out a little bit more. So, like this, for instance, space it out a little bit more. Then it's more the nitty gritty details that we maybe don't have to worry about right now. Here too, for instance, this, not sure if it's so good to manufacture this with these small copper I don't know, maybe I can do zones and then add a zone cutout. So for instance here, around this area. Maybe just this entire area. Is that how you should do it though? If you want to omit some parts of the PCB having copper at all, or if it's better to just leave it like that. Ground. Oh. Okay, so no errors there. Primary, secondary. Feedback. just play around with it a little bit, switching. Controller. So input, primary, secondary, feedback. Switching. We can always just, yeah, do a little bit more now and then change it later. I don't love this part. I think it would be nicer to kind of make a little bit more space around. Maybe apart from this here, can make still close, rather close. This the coupling capacitor. Same with this one. All these things can maybe be a little bit further away. And then the vias, of course. Other than that, it's quite solid, I think. Load, put it here. It's not pretty. Here, maybe? No. Has to be like this, even though. Feedback. Yeah, so we have one trace on the bottom layer. This trace. That we can also fix, maybe. My tea should be done. What if on the bottom layer we also put a, so maybe here. Or bottom still screen, I mean. Sorry. Not potential. What? Until I get a nice logo going. Just put it on the bottom like this. And then maybe, how would that look? Here. We put bottom silk screen. AC/DC flyback converter. Something like that. For fun. Check the bottom. This is upside down. Wait, we should have this on the front though. Looks cooler. Let's put it on the front. Move. Alright, oops. Didn't mean to do that. Can I not? AC/DC quasi resonant Y back converter version 1. Now it's kind of looking like something now. I don't like the placement of this. I think it would be nice if I could have that also at the center. Or maybe change these terminals into some banana jacks or something. So it looks a little bit nicer again. It would still work with these. And then one at the bottom, nothing. I think that looked cool. Cheers. Yeah, we're making progress. Been streaming now for 31 episodes already. Working all the way from concept stage, so drawing this up in a Mira board and doing component selection, calculations, rough planning, rough system design, understanding how an AC/DC switch mode power supply works, and the more specific quasi-resonant type, which is a flyback converter. I also want to build a forward converter, which I think transfers doing the on time, while as in a flyback converter it transfers energy in the off time of the switching element. So I think that would be cool to also try out. But I have some other ideas for a little bit simpler, a little bit lower voltage, also some constant current LED drivers, LIN modules, maybe even some CAN modules as well. I'd love to make a full network of LIN nodes, CAN, maybe other components as well, or other type of communication protocols like Ethernet. Ethernet, I would love to design at least a network, a point-to-point, maybe not a bus or anything like that, but maybe we'll see in the future. Yeah. I don't feel like I'm done, but I feel like I've gotten quite far with this. As you can see, it's not perfect, but it doesn't have to be either right now, because I won't be able to get this manufactured right now. In the future, yes. Come on now. Whatever. It feels nice to put my name on it too. Or this community's name. So this is what we will be building together. I mean, it doesn't seem like much, but after 31 episodes where I've been working between 2 hours, 3 hours at a time, I put in some time into this, and I have to be honest, I think I'm confident enough that this could be manufactured, and it could probably work as well. I dare say it, but I won't be able to do that right now, to test it out and stuff. So in some upcoming videos, I will start a new project, and then I will put this project a little bit on hold. We're not done with power electronics, but we're gonna also work with some new ideas, trying out a bit different things, some smaller PCBs that we can order and test and also program. And I think it would be cool to make a lean network with some light modules and see how that works. With a bit lower voltage. Yep. And then I will also work on a little bit more on a more, you know, design or a development plan. So set up a development plan, how I start with a concept and how I work towards production. So that will be part of these episodes as well. Maybe a little bit more preparation from my part, and then during stream I will do the actual design and or execution of my preparation. But yeah, what it's all about is to get things moving, design PCBs, and eventually order them, test them, prototype them, test them, write the software for them, and show it all on stream. And also making some cool videos about it in the future. I like that idea of making a video about my journey designing this AC/DC power supply. And I can't wait to test it, because I will be able to test it in the future. Right now I'm just pondering a little bit on my next moves. So if this is the first version, obviously it's not perfect, but we can make it better. And I think a good approach would be to take basically what we have right here. Take what we have right here and move things a little bit more symmetrical. That would be nice. I want the input connector here and move everything a little bit more down. We have a lot of space down here, so we can probably move this controller part further down into maybe this area, the switch maybe, but also further down here. It's a lot of dead area right here. The output part, whoops. The output stage or the secondary side as well. But that one is pretty much, I mean, I don't see a better solution right off the bat, at least, how this should be laid out. Any different? If you have any tips, let me know in the comments or in the chat. But that will be my next, I think. I would like the transformer more in the middle. Move this down further. Move everything a little bit down. And then this input terminal bit down. Do, 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 do. And I also want it black. Actually, I think it's cool. And we should do what we like, what we want, right? So it would look more like this then. This trace right here. VS I need to fix. But hey, this is version 1. If you like this stream and this video, please give a like on this video. Also subscribe to the channel. Really appreciate it. I'm gonna build a community of engineers, hobbyists, professionals, amateurs, whatever, people that are interested in electronics. We're gonna do a lot of exciting things, learn a lot of exciting things. But now I'm in a bit of a okay, I will have a little break. Just think a little bit for myself here. I'll be right back. Okay, I think that I made a decision. I'm gonna end the stream for today. This is this is developer potential, and we're designing electronics from concept to production, and we just finished version 1 of the AC/DC quasi-resonant flyback converter, which is quite the achievement. It was a lot of fun working on this project, and I'm not entirely finished here. But I only have a few minor things to do on the design before I would consider it quite good, or at least finished now. And then I will put a pause on it until I can pick it up again on the new year. Before that, I will start with another project, which I don't know yet exactly what it will be, but I'm pretty sure it will be a LIN module. So you can think of it as a, where you mean, it could be an automotive component. It could be another type of component that uses LIN. It will be an LED module. I'm pretty sure. So we do a simpler project and we talk through the design and all the way from concept to production. And that is what is fun. That's how we learn, and that's how we build production worthy stuff. Yeah. Pleased to have you here. Thank you for watching, and until next time.